Hello, everybody. Okay, you're living in the 1900s. You're playing this new craze game. It's called pushball. It's a variation on tug of war, I guess, where you've got to get this huge ball across the line into the opponent's space, and the winning team is the team that does that first. So you're coming up with your strategy as to how you might do that. Now, I think you've got a couple of options. The first one, which I've drawn for you, it is literally to push as those two arrows are showing. And I think that's going to generate what we call translational motion, which basically means the object is going to move either to the left or to the right. It depends who applies the biggest force. There's going to be no rotational motion at all if you apply the forces as shown. Why is that? Well, we can explain this from our idea of moments. I don't think there is going to be a turning force from either team. Why is that? Because if I just kind of draw the lines of action of the two forces and compare that to where the pivot is, which is the center of mass of the spherical object, there is zero distance between the line of action of the force and the pivot. So in other words, there's no moment, there's no turning force. So it looked like the red arrow, Team Red, was applying the bigger force compared to Team Blue, so the object is basically going to move to the left. And that would be probably the most efficient way of achieving that outcome. I guess you could apply the idea of moments. And if both teams kind of pushed, as shown on the diagram now, each team would be providing some kind of moment because there's the pivot and there is the line of action of the forces. And remember, we kind of draw our dotted line through the pivot parallel to the line of action. Now there is a distance, isn't there, between the line of action of each force and the pivot. So Team Red, they're applying an anti-clockwise moment. Team Blue, they're applying a clockwise moment. It now comes down to who can apply the biggest moment. Either strategy would work, the first strategy being the most efficient. Why put lots of energy into causing objects to turn when you can literally just move them from left to right? However, there is a third option which nobody in their right mind is going to choose, and that is the option being shown to you now. If you were to apply that strategy, that object would not move left or right at all. All it would do is it would rotate, okay, and it would rotate clockwise. We would have pure rotational motion, and no translational motion. And that's the subject that we're going to have a look at today, to do with couples and torque. So how do we get an object then to move purely rotationally? So here's an object, a bit like the corkscrew on that PowerPoint slide that has just changed on the left. And the first bullet point says that there are three conditions that we need to have in place for rotational moment. And that is, we have to apply what's called a couple. Okay, what does a couple mean? It means a pair of forces equal in magnitude, opposite in direction, perpendicular to the distance between them. And if we can satisfy all three of those conditions, we have what is known as a couple. So let's draw a couple then. I mean, couple implies two to us, doesn't it? So there are your two forces. Okay. Are they equal in magnitude? Yes, they are. Are they opposite in direction? Yes, they are. Are they perpendicular to the distance between them? Okay, so let's draw a line between them. And yep, both of those forces are perpendicular to the distance between them. So we have got then the conditions necessary for rotational motion. We have a couple. And the size of this rotational force that's produced is what we're going to call a torque. And I think of torques as being really a special case of moments, because if we sum up the total moments acting on this object, then we've just calculated the size of the torque. Now, there is something that you need to notice with respect to these two forces. This force here is providing a clockwise moment. This force here is also providing a clockwise moment. And this is one area that distinguishes torque from moments more generally, because when we applied the principle of moments, we always had some anti-clockwise moments and some clockwise moments, and they were equal to each other, weren't they? Equal and opposite moments. Here, we've only got clockwise moments, and that's going to lead to clockwise rotation. Similarly, if we only had anti-clockwise moments, that would lead only to anti-clockwise motion. Okay, so if it's true then that torque is the sum of these moments, let's calculate what that is. Let's work out what the sum of the moments is. A moment is force times perpendicular distance between the pivot and the line of action of the forces. So I'm going to call that d by 2. Okay, the force on the left then is providing a clockwise moment of magnitude F times d by 2. And the force on the right is similarly providing a clockwise moment magnitude force d by 2. In other words, if we sum up the total moments acting on that object, it's F times d, and that is what we are going to refer to as the torque. Okay, we would say the torque of a couple is equal to force times distance. Now, this is where we need to be a little bit careful now on what we mean by both of those things. So the force is not the total force. So in other words, if this is 10 newtons and this is 10 newtons, the value that you would put in at this point would be 10 newtons. You wouldn't add them up. It's not the total amount of force, it's the magnitude of each force. And remember, they've got to be equal to each other to be a couple. And then distance is the distance between forces. And again, that's different to when we talked about moments, because the x in the moment equation was the distance from the pivot to the line of action of the force. Okay, here, d is the distance between the forces. Okay, so that bar in orange is going to rotate clockwise. Why? Because there's a couple acting. Two forces, equal in magnitude, opposite in direction, perpendicular to the distance between them. We have that couple, and therefore we're going to get a rotational force, and the size of that rotational force is what we mean by torque. So, straightforward calculation. You're simply going to multiply the 20 newtons by the distance between them, which is 46 centimetres or 0.46 metres. Okay, that would be a very straightforward calculation to do. Now, examiners quite like getting you to identify which forces are acting as couples. And in front of you, you've got 4 options, and we're being told that diagram A is the correct choice. Okay, so let's rule out why it's not B, C, and D then, and then we'll have a look at A specifically. Okay, so looking at B, we've got 2 forces. They are not equal in magnitude, so already we can rule that out as being a couple. And similarly for C, they're not equal in magnitude. Okay, when we look at option number D, the distance between those forces is not perpendicular. In other words, they're kind of acting in different directions, but they're not acting in opposite directions. So we're left with A. So let's go through our 3 criteria. They have to be equal in magnitude. They are. They have to be opposite in direction. They are. And they have to be perpendicular to the distance between them. And they are. Okay, so despite the fact that one of those forces is acting from the kind of circumference of the circle and one of them's acting from the centre of the circle, okay, to act as a couple, it's those 3 criteria that need to be met. Okay, what if we have forces at angles? Now, this is very similar to some work that we've done with moments. So let me redraw the diagram that you've got then with the forces correctly shown. So there are your two 4 Newton forces. And there's the pivot in the centre. And we're told that we've got a 30-degree angle between them. Now, what's important then is the perpendicular distance between the force and the pivot. Okay, so in other words, we want to know what component of that 4 newtons is acting perpendicular to the line between those two forces. So if we think about the right-angled triangle that we've created, effectively we are looking at the opposite side, aren't we, of the triangle. So this would be 4 sine 30, and obviously this also has to be 4 sine 30 because they have to be equal in magnitude. So when you're working out the magnitude of the torque then, you would multiply the force, which is perpendicular, multiplied by the distance between those two forces. And the question says that we've got a ruler of length 0.3. So we will assume that that is the entire length of that ruler. And that is how you work out the torque for forces which are acting at angles. Now we can link what we've looked at here with torque with moments. And here's a good question where you've kind of got moments and you've got torque. So let's just recreate the diagram. So have we got a couple? It looks like we do, doesn't it? Because we've got 2 equal and opposite forces perpendicular to the line between them. So those two 50 Newton forces are acting as a couple. So let's work out the torque. Force times distance, 50 multiplied by, now we've got to get the right piece of data here. It's the length of the beam, which we want, 0.6 meters. So we've got 30 Newton meters. Now we haven't really talked about units of torque, but the units of torque are the same as for moments because it's force multiplied by a distance. So we've got 30 Newton meters of rotational force, and it's going to be in the clockwise direction, isn't it? Okay. Now the question says that we have got a piece of rope and it seems to be kind of wound around this kind of like spindle, and we are applying some kind of tension. And if you imagine what's going on here, that's going to apply a moment, not torque. Why is that? Because we've only got one tension force. We don't have a couple acting at the centre there. So that tension is applying a moment. And I think if you imagine yourself pulling on that piece of rope, that is going to try and provide an anti-clockwise moment. And if we go back to the question, it says calculate the minimum tension needed to prevent rotation. Okay, so here's what we're going to try and do here then. We are going to try and balance the 30 Newton meters of torque with an equivalent amount of anti-clockwise moment. So we need 30 Newton meters of anti-clockwise moment, and that's what the tension's going to provide. So how do we work out the moment? It's Fx. Remember, got to be careful between our D's and our X's. So we've got 30 Newton meters of moment to provide from some amount of force on that piece of rope. And the X is the perpendicular distance from the line of action of the force to the pivot. That is the other piece of data, isn't it? That is, hang on a second. That is the, I'm doing a good job here. There we go. That is the radius of disc. That is the 0.12 meters, isn't it? Okay, that is that distance in there. Okay. And that means we have a force required of 250 newtons. So if I pull on that rope as shown with a force of 250 newtons, it is providing a 30 Newton meter anti-clockwise moment in order to prevent rotation because we've got a clockwise torque of 30 Newton meters. So we are applying an equal and opposite amount of anti-clockwise moment to counteract the clockwise torque. So you've got moments and you've got torque in the same question. Okay, finally, let's just have a quick look at kind of application of this. So if you've watched any kind of big Hollywood films, helicopters in a kind of war zone, one of the strategies is to take out what we call the rotor fin, not the main blades, but the rotor fin at the back of the helicopter, and then you watch that helicopter going into a kind of a tail spin. So if I just recreate what you've got in front of you, there are the rotor blades of the helicopter. Okay, and at the back here, we've got the rotor blade. Okay, so we've got a smaller set of blades at the back. Okay, the blades are turning anti-clockwise. Okay, so how is that being achieved? It means that the blades are providing a couple. Equal in magnitude, opposite in direction, perpendicular to the distance between them. So in other words, we are going to get a torque in the anti-clockwise direction, okay, as those blades spin around. Now, Newton's third law says for every action, there's an equal and an opposite reaction. So as the blades push against the air pushes back against the blades, and we get a clockwise reaction force. And that means that the body of the helicopter is going to start rotating in a clockwise direction. And that's not going to be helpful. So the solution then is to provide not a couple, but a moment from this rotor. And this rotor provides a force in that direction. So there is the pivot. There is the force. The rotor is providing a moment. And it's providing a moment in the anti-clockwise direction. Okay, and it is counteracting the clockwise torque from that reaction to the blade spinning. And it's very similar to the example that I showed you before, but more of a real life example again of how torque and moments kind of link together.